Welcome to the Universe Effect's first episode of Thought Experiments, where we will try to give you the lowdown on unique theories in about 3 minutes. I'm JP, and today we will be exploring time dilation. Brace yourself for the definition of time dilation. According to Webster's dictionary, it is a slowing of time in accordance with the theory of relativity that occurs in a system in motion relative to an outside observer, and that becomes apparent especially as the speed of the system approaches that of light. What this means is that as you approach the speed of light, time will pass more slowly for you. But how does this work? First, we need to get a few things straight. There is no absolute motion or rest. Objects only move relative to each other, and the speed of light is the same for all observers. To demonstrate this, let's visualize a blue train that is stationary, and a red train that is moving at a constant velocity. Clearly, when we are standing still, the red train is moving forward. But when we move with the red train, we gain a different perspective, and now the blue one appears to be going backwards. There isn't one correct conclusion because there is no way of telling which one is right. Each different viewpoint has its own frame of reference. Now let's look at something called Einstein's Clock. Let's visualize two mirrors at rest facing each other in space. A light beam is bouncing back and forth between the two, and a line is tracing the path of the photon. Let's call the time for the light beam to bounce back and forth between the mirrors T1. When we move the mirrors at a constant speed, the light has to travel a greater distance, so it takes more time for the photon to bounce between the two mirrors. Let's call this new time T2. Now let's look at the frame of reference from an observer moving with the clock. Let's call him Shane. So if Shane is moving with the clock, his frame of reference tells him that the clock isn't moving at all. But we must remember an essential rule: the speed of light is the same for all observers. This means Shane sees the photon bounce back and forth just like if the clock wasn't moving at all. And it doesn't take extra time for the light beam to bounce back and forth. So Shane sees the photon bounce back and forth with T1, but we see the photon bounce back and forth with T2. So it takes more time for us and less time for Shane. Another thing happens to the clock though: it shrinks. To visualize this better, we should increase the speed of the clock. Let's imagine the clock moving close to the speed of light. So here's what the path looks like from our perspective. To keep track of all the variables, let's label the diagonal component D, the horizontal component dx, and the vertical component dy. So we can conclude that d is larger than dx and dy. Unfortunately, when you derive the velocity from the distance traveled and the time taken, it is greater than the speed of light. To fix this, we need to shorten the distance between the mirrors. The clock shrinks, which means that dy decreases, and then d becomes shorter. dy shortens until the velocity equals the speed of light. Time dilation and length contraction are both side effects of the speed of light. But don't these theories only apply to photons traveling at the speed of light? No, and here's the reason. Information is energy, and energy cannot travel faster than the speed of light, so therefore not everything happens at the same time. This is the fundamental part of why time dilation works. Let's picture a person standing on the Earth. Call him Timmy. Suddenly a giant solar flare occurs on the sun. It takes light about 8 minutes to reach the Earth, and you can think of the information coming from the sun as an explosion. The information explosion hasn't reached Timmy, so therefore the solar flare hasn't occurred for him yet. One of our rules in the beginning of the video was that the speed of light is the same for all observers. Light isn't just the fastest thing in the universe because it's light. It has to do with the electromagnetism in the wave. But this is also part of the reason information can't travel faster than the speed of light. But it seems that we've ran out of time, so I guess that's a discussion for another day. Feel free to rewind this video. There was a lot of information packed into a short time. But if you liked it, don't forget to check out our monthly podcast and last week's video about gravity. Thanks for watching, and if you want to see more like this, subscribe to the Universe Effect. Somewhere, something incredible is waiting to be known.